Today I'd like to look at uncertainty and time dependence. We talked about time dependence last time in solving the Schrödinger equation. I want to bring uncertainty into this, but I'm going to motivate this by examining systems that have more than one variable or more than one dimension. So some examples. Suppose I have a particle in three-dimensional space. I'd need three position coordinates to describe the location of the particle. Or I could be talking about a system that has two physically independent spins. You know, maybe I'm looking at the z components of two separate particles, independent of one another. Let's start with that two-spin example. We'll associate one z component with one operator and another z component with the other operator. So let's say that our two spin operators are L and M. I'm going to have, in this case, if I measure both spins, the system ends up in a state that's simultaneously an eigenvector of operator L and an eigenvector of operator M. So I need two sets of labels for my basis vectors, and for now I'm going to call them lambda sub I, and I'll call them u sub A. Those are going to be my two labels. I'll get rid of the labels later. But this is going to be these are going to be simultaneous, that is to say, lambda sub I ket and u sub alpha, u sub A ket are going to be simultaneous eigenvectors of L and M. What that means, of course, is that L operating on lambda I and on UA will be equal to eigenvalue lambda sub I UA. Similarly, M acting on lambda sub I and UA will be equal to eigenvalue mu A lambda sub I mu A. And at this point, we can probably drop the subscripts. So what we're going to have is, let's make it just lambda mu, and we'll have lambda mu, like so. Okay, so these are going to be the two equations that we need. This is telling us that we have simultaneous eigenstates of operator L and operator M. Now, in order that they be simultaneous eigenstates of both operators, it must be that L and M must commute. That is to say, L and M operating on lambda and mu must be equal to M, L operating on lambda and mu. Or I can say, in commutator language, the commutator of L and M times lambda mu must be 0. We call L and M a complete set of commuting observables. Sometimes you'll see the abbreviation, for example, in Kohn-Tanucci's very comprehensive quantum mechanics book, you'll see it written this way: complete set of commuting observables, something like that. So it's important that these two guys commute if they're going to have the same set of eigenvectors. I want to bring in another concept from quantum mechanics at this point, and we'll touch on it a little bit here, then we'll go deeper into it in the next section. And that is the notion of wave functions. Probably from your modern physics class, you were exposed to wave functions. In fact, you probably heard the term wave function long before you heard the term ket in your life. This is the way we're going to explain wave functions. Suppose I have a basis of states for a quantum system. Let's suppose the orthonormal basis vectors are A, B, C, D, onward ket. And let's say that you have corresponding eigenvalues, A, B, C, D, and so on and so forth. If I have any arbitrary state vector, psi, I can expand that state vector in terms of those basis vectors. So I can write psi as the sum over A, B, C, etc. Psi of, just go A, B, C, times ket A, B, C, and of course we can go up as high as we want to go in the alphabet. And I can write psi of A, B, C as ket A, B, C, psi. So inner product of each of those kets, I should say bras, with psi. We call psi of A, B, C, etc. the wave function of the system in the basis defined by A, B, C, etc. kets. So you notice, when I have a ket, it's independent of the basis in which I'm working. If a ket is a ket is a ket. But when I'm talking about a wave function, the wave function depends upon the basis in which I'm talking about. In this case, I'm talking about the basis that has eigenvectors or eigenkets A, B, C, D, etc. Let's say a little bit more. I can write, and you probably remember this expression from modern physics, I can write the probability of the particle being in, let's say, state ABC as psi star of ABC psi ABC. Oh, I should probably use capital letters since I've been using capital letters all along. I'll use the capital letter. The form of the wave function, though, depends on which observables we're focusing on. So, for example, psi of mu, going back to the original case, would be written as mu bra psi, so the inner product of mu and psi. If I want to go, in fact, let's say we want to go with the, suppose we're talking about z spin, spin in the z direction, the up case. All right, let's do that. Up, and then psi in the down case, I could write as psi of d is equal to d psi. And that would define a wave function in the up-down or sigma sub z basis, because sigma sub z is the operator that pertains and has the eigenvectors up and down. On the other hand, suppose I was in the right-left basis, or the sigma x basis. Suppose I'm in sigma x, then I would be talking about psi of r is equal to r psi. Psi of L is equal to L psi. That's because in this case I'm in the sigma sub x base. I'm worried about spin in the x direction. In addition, if I sum over A, B, and C, psi star of A, B, and C times psi of A, B, and C will equal 1, so long as my wave function is normalized. Let's talk about then uncertainty. Suppose I have some observable A, and I call its eigenvalues little a. If I take the expectation value of operator A, of course, this is what we think of as just an ordinary average. In other words, I could write that as sum over A times the probability of being in state A. We would expect that P of A would be centered upon the expectation value. Any uncertainty that I have in this measurement, in this observable A, is going to be reflected in a standard deviation. Let's define A bar as operator A minus the expectation value of A times the identity operator. The eigenvectors of A bar will be the same as the eigenvectors are for A operator. The eigenvalues are going to be shifted so that their average is 0 as well. So I can write A eigenvectors is A minus the expectation value of operator A. My standard deviation is written as delta A operator squared, which I can write as sum over A bar squared, P of A, which is the sum over A minus expectation value A quantity squared times P of A, or delta A squared is equal to psi A bar squared psi. That is my standard deviation. By the way, if expectation value of A is 0, then of course my standard deviation is just psi A psi. In this case, we'll assume that it isn't. We're going to base our uncertainty principle, though, on something that we call the triangle inequality. We'll try to motivate it like this. Magnitude of x plus the magnitude of y is always going to be greater than or equal to the magnitude of x plus y. You may have seen this in other places before, but we can make it apply more generally. We can say, of course, the sum of the legs of any two triangles will always be bigger than the third leg. So we can write it this way. If x, y, and z are the sides of a triangle, we can say that this is indeed the case. And or we can just write this again as x plus y. Let's do this though. Let's square this equation. X squared plus y squared must be greater than or equal to x plus y quantity squared, which of course is going to be equal. So this is telling me that and this is, sorry, x squared plus 2x y must be greater than or equal to x plus y quantity squared. This tells me that And on the right-hand side, this becomes x squared plus y squared plus x dot y. Get rid of the two x squared plus y squared, and what do we get? We have magnitude of x times the magnitude of y is greater than or equal to x dot y. This is another form of the triangle inequality. And it's not really a surprise because this quantity x dot y is like saying magnitude of x, magnitude of y times the cosine of the angle between them, and the cosine can never be greater than 1. So this kind of makes sense. I want to use this form. X squared y squared greater than or equal to x dot y squared. So this is what we call the Cauchy-Schwarz inequality. So what I've done is square both sides, the previous expression, and we see that we got x squared y squared is greater than or equal to x dot y squared. Now for complex vector spaces, it's a bit more complicated because x is equal to the square root of x times x. The same thing for y is y. And x plus y is going to be equal to the square root of x plus y times x plus y. So what we get then is x plus y is greater than or equal to x plus y. If I square it and simplify both sides, I get 2x y is greater than or equal to xy plus y x. To get to a general uncertainty principle then, what I need to do is define ket x as A operating on psi, and ket y as defined as B operating on psi. And using the previous inequality, this says 2 times the square root of A squared, B squared, is greater than or equal to psi commutator A and B times psi. And if we supposed that expectation value of A equals B equals 0, it's even simpler. We get delta A, delta B is greater than or equal to 1/2 psi commutator A and B psi. This is what we call the generalized uncertainty principle. And we'll see the first place that we will apply it will be in our next lecture when we talk about momentum and position. And so let's pick up with that next time.